recap, we were talking about Brownian motion, which we represented as B, and we know that this Brownian motion is a continuous time stochastic process, which is a function of t. And the reason why we use it is because we want to add randomness to our model to essentially represent real-world stock prices more accurately. So going off of that, we have our differential equation that represents our drift. And essentially we want to add some random stochastic shock to this. So this is going to be our shock. And our B is obviously going to be Brownian motion, which is a function of time. So again, the last video we discussed the properties of Brownian motion, and in this video we are going to go over a graphical representation of what Brownian motion really is. So just to start off with, I want to write B of t in this form. I want to say at any time t, it is a normal distribution. It's a random variable that has a normal distribution with mean 0 and variance t, or I can also write this as a standard deviation of square root t times the normal distribution of mean 0 and variance 1. Okay, so let's represent this graphically. So over here I have my Brownian motion, or B, as a function of time, and then over here we have time. And our first property of Brownian motion states that we are going to start at time equals 0. So here's where our first point is going to be. And the second property states that if I subtract 2 increments of my Brownian motion, I'm expected to get a normal distribution. Obviously with a mean of 0, meaning my expected value of my Brownian motion is going to be 0. So let's try to represent that. So if I have my next point, which I'll say is 1, right? So essentially what I'm going to do is create a normal distribution like this, and essentially I'm going to sample my next point from this normal or Gaussian distribution. So my expected value of B of t is going to be 0 again, and I'm just going to denote this as my expected value of B of 1, for example, right? And just as a side note, I want to say that my expected value of B of t is going to be 0. But essentially what I'm going to do is sample this and say, let's say I get this point, right? So my next point, instead of being 0, is going to go here. So here's my next point. Now, if I'm going to sample 2, I'm going to create the same exact normal distribution, but starting from this point right here, from the value I got at B of 1. So let's create that normal distribution, and let's say I get this point over here. Even though I'm expected to get this point again, let's say I go up here. And then at 3, I can sample the same normal distribution with the same exact variance. And let's say I get this point over here. And I can repeat this process indefinitely until I get to a final stopping time. So if I were to repeat this process and just make my increments smaller, I could get a sample path that looks something like this. And obviously, negative values are allowed. So I could get something like this. Now, to further illustrate this point, I don't have to get a path like this. If I wanted to start at this point, and if I want to do another Brownian motion and randomly sample, I could get values like this, for example. Or I could get something like this. So all of these are possible paths for my Brownian motion. So on and so forth. Cool. Now that we got that out of the way, I'm going to draw another illustration just to further illustrate how Brownian motion behaves. And I want to focus on a slightly different property in this scenario. So instead of a normal distribution, let's say I can either sample from -1 or 1 and nothing in between. So let's say my B of t is going to follow either -1 or 1, each with 50% probability. Cool. So let's say I start at 0. And then at 1, I can either go up to 1 or -1. And then from 1, I can either go up to 2 or 0 again. And I can do the same thing with this point. From here, I can go up or down. I can go up or down. And yeah, so on and so forth. Right. And let's say this is my time increment at 1, 2, 3, 4, so on and so forth. Cool. So if I were to extend this to a normal distribution of 0 and 1, right? At time increment 1, if I were to start from 0, if I were to take b of 1, then I would be in a 1 standard deviation interval of getting a point in this region right here. So this happens with a 1 standard deviation, or 64% probability of b of 1. So my b of 1, I would stay between, let's say, square root 1 and Yeah, so essentially I'll stay between plus or minus square root 1. Now, if I were to take b of 2, for example, then I have the same probability of staying within plus or minus square root 2. And if I were to take b of 3, then I'll have a 1 standard deviation probability of staying between plus or minus square root 3. And to illustrate this, in the general case, if I take b of any time t, I have a 64% probability, or 1 standard deviation probability of staying between plus or minus square root of t. And that point is illustrated through this discrete random walk. Cool. Now let's put this back into the original graphical representation of Brownian motion. Essentially, at every point t, I have a t standard deviation. So my 64% probability, or my singular standard deviation, is actually a function of time. And it's going to look something like this. Where this is going to be square root t and negative square root t. So if I were to have random paths using my Brownian motion, at time equals 5, I would have essentially a 64% probability of my Brownian motion finishing in this region right here. Now, on the other hand, if I were to look at the case of 2, for example, I would have the same probability of my function finishing over here. And I can repeat this process for a time increment of 3, a time increment of 4, 5, and so on, and so forth. And just to make it clear, this is going to be my t. This is going to be my Brownian motion as a function of time. Cool. Now, I would like to illustrate another point, and this is important for continuous time stochastic processes. And let's go back to our random walk. Let's say we start over here, and then we're going to go up to this point, then down to this point, and then we're going to go to this point over here. Let's say this is, we technically start at 0, so say we go here. And let's say this is 1, 2, 3, and 4. This is my time axis, and this is my Brownian motion. Cool. So we have a slope, right? And this is going to be our delta t, and this is going to be our delta b. And in the same way, we're going to have a slope over here, which again is our delta t and delta b. In this case, it's negative, and obviously we'll have a slope over here, so on and so forth. Now, Brownian motion is a continuous time stochastic process, meaning the points between 1 and 2, or 2 and 3, or any 2 points don't exist. So to represent this graphically, let me change this to I, 2I, 3I, 4I. And in this case, let's say I is equal to 1. And then we're going to have our change in b over change in t, which is going to be our slope. Okay, when I is equal to 1 by 2, then that means our denominator gets cut in half. So this is 1/2 delta, our original delta t, which would mean we have 2 times our slope. Now, if I say I is 1/4, if I cut this even more, then I would have 4 times my slope. So this reveals something. There's a pattern here. If I say I is equal to 1 over n, then that would imply that my slope would be my n times my original slope, my slope being I of 1, right, or just dB dt. Cool. Now, what if I take the limit as n goes to infinity of 1 over n? Well, that would essentially mean that we have 0. But what does that imply? That means our n times slope would approach infinity. So graphically, what does this represent? As we take n to infinity, we're essentially pushing all our points closer and closer together, such that it becomes a continuous time, meaning the exact next point after I would be essentially 2I, but 2I is numerically the next number after I. And when we do that, this slope will keep increasing and increasing until graphically we almost get a vertical line. So let's say this is our 2I, and 3I, 4I, 5I, so on and so forth, right? So this is what happens when we take n to infinity. So this implies that our dB dt does not exist. This is interesting because b of t is continuous on the interval 0 to a final time, but b of t is also non-differentiable on the interval 0 to t. So essentially what we have is a continuous time process which cannot be differentiated, which will make analysis quite difficult. And obviously, if we can't differentiate with regular calculus means, then it'll be that much harder to integrate. But there's a way around this, and this is also a theorem that I will not prove. There's a very extensive proof, but I'll just state it. It's very simple. It's called the quadratic variation of Brownian motion. And essentially what this states is when I have dB, that's actually equal to my square root of dt. And another way to write this is dB squared is equal to dt. Cool. In the next video, we will be discussing some more parameters that we can add into our Brownian motion before we add it back into our model that incorporates drift to complete our model of the financial asset.